Alrighty, so this is your third and final installment of buffer calculation cheat codes. Now the first two, they were for when you're creating a buffer. So either you're just mixing the weak acid and the salt of that weak acid, just basically the mixing the ingredients. The second one was where you create a buffer again, but this time you react a weak acid with a strong base. Now, the third type of question you're going to get is where you have a buffer already and you know the components. It's just we're adding either an acid or an alkali to it, and we need to find out what the change in pH is going to be. So for example, in this question here, a student prepared a buffer solution by adding 0.0136 moles of a salt to 100 centimeter cubed of 0.5 molar of a weak acid HX, and he mixed it thoroughly. So they've created a buffer already. Now we know the number of moles of salt. We can easily find the number of moles of weak acid by using concentration times volume here. Next up, we can see that the student has added 3 times 10 to the minus 4 moles of potassium hydroxide. Now that is a strong base. The question is, calculate the pH of the buffer solution after adding the potassium hydroxide. But before we get into the numbers, really important, give your answer to 2 decimal places. Now, what I tend to do when I see something like that, whether it's to appropriate significant figures or something, I put it at the bottom next to the answer so I don't forget. So first job here is to write out our equation for our buffer. Now this basically just shows the dissociation of the weak acid, HX, going to hydrogen ions and X minus. First job, how many moles of acid and salt do you have in the buffer solution already? The acid I've calculated using concentration times volume. The salt is given to us in the question. Then we add our potassium hydroxide. Now remember, the question tells us that we're adding 3 times 10 to the minus 4 moles of that potassium hydroxide. Now that potassium hydroxide reacts directly with the weak acid. It's a 1-to-1 reaction. They won't give you anything different. So what I'm doing here is I'm taking away 3 times 10 to the minus 4 moles of the acid because that's how much of it is going to react with the potassium hydroxide. And when it does, it creates 3 times 10 to the minus 4 moles of our salt, X minus. So now we have the new number of moles of weak acid present in the buffer and the new number of moles of salt present in the buffer. Next step is to find their new concentrations, and that's because we need concentrations in order to plug those into our Ka expression. So the total volume here, because everything else was solid, is still 100 centimeter cubed. So new concentrations are those numbers of moles divided by 0.1. Shting! Now we've got everything we need for our Ka expression. We've got Ka given in the question, and we've got our new concentrations of Hx and X minus. A quick rearrangement, plug your numbers in, then all we need to do is plug our hydrogen ion concentration into the pH expression. So in this case, we added a strong base. That's going to reduce the number of moles of weak acid you've got and increase the number of moles of salt. Of course, the opposite is true. If you add a strong acid, that's going to reduce the numbers of moles of salt that you've got and increase the number of moles of weak acid. So it's the opposite to this. So all in all, don't forget there are 3 different types of buffer calculation. First one, where you create a buffer just by mixing the weak acid and the salt. Second one, again, when we're creating a buffer, but this time we're reacting a weak acid with a strong base to create some salt. And then thirdly, you could be given a buffer solution and then asked to find the new pH after a strong acid or a strong base has been added.